Welcome to this comprehensive overview of data cleaning techniques. In the world of data analysis and machine learning, the quality of your data directly impacts the reliability of your results. Understanding how to effectively clean data is a fundamental skill for any aspiring data professional. Data cleaning is the essential process of identifying and correcting errors, inconsistencies, and inaccuracies within a data set. It involves a series of steps to ensure that your data is accurate, complete, and ready for analysis. This foundational step is crucial for transforming raw, often messy, data into a usable format. The importance of data cleaning cannot be overstated. It forms the bedrock for reliable analysis, ensuring that any insights derived are based on trustworthy information. Clean data enables informed decision-making, leading to more effective strategies and better outcomes in any field. Without proper cleaning, even the most sophisticated analytical models can produce flawed results. Conversely, the consequences of poor data cleaning are significant. Unclean data can lead to skewed analyses, where patterns and relationships are misinterpreted. This often results in misleading conclusions, causing businesses and researchers to make incorrect decisions. Ultimately, poor data quality wastes valuable resources, as time and effort are spent analyzing unreliable information. One of the most common challenges encountered in real-world datasets is missing values. These occur when no data is stored for a particular observation or variable. Missing data can arise for various reasons, such as data entry errors, equipment malfunctions, or respondents choosing not to answer certain questions. Addressing missing values is a critical step in data preparation. Several techniques are available, each with its own advantages and disadvantages. The choice of method often depends on the nature of the data and the extent of the missingness. One straightforward approach is deletion. This method involves removing entire rows or columns that contain missing values. For instance, if a record has a missing entry for a crucial variable, that entire record might be discarded. The primary advantage of deletion is its simplicity. It is easy to implement and ensures that subsequent analyses only use complete data points. However, a significant disadvantage is the potential for substantial data loss. If many records have missing values, deleting them can drastically reduce the size of your dataset, potentially losing valuable information and introducing bias. Another powerful technique is imputation, which involves replacing missing values with estimated values. This approach aims to preserve the dataset's size and statistical power by filling in the gaps rather than removing them. Imputation methods range from simple to highly complex. Among the simplest imputation methods are mean, median, or mode imputation. Here, missing numerical values are replaced with the average or middle value of the observed data for that variable. For categorical variables, the most frequent value, or mode, is used. These methods are simple to implement and computationally inexpensive. However, a key limitation is that they can distort the data distribution. Replacing many missing values with a single central tendency can reduce variance and weaken relationships between variables, potentially leading to biased estimates. A more sophisticated approach is regression imputation. This method predicts missing values using a regression model based on other variables in the dataset. For example, if a person's income is missing, it might be predicted using their education level, age, and occupation. Regression imputation can capture more complex relationships within the data, providing more accurate estimates for missing values. However, it requires careful model selection and validation. An incorrectly specified regression model can introduce its own biases and errors into the imputed data. K-nearest neighbors, or KNN, imputation is another effective technique. This method replaces missing values with the average of values from the K-nearest neighbors. The neighbors are determined by calculating the distance between data points based on their observed features. KNN imputation is particularly advantageous for datasets with complex relationships, as it considers the similarity between data points. It can handle both numerical and categorical data effectively. However, it can be computationally intensive for very large datasets. Beyond missing values, another common data quality issue involves outliers. Outliers are data points that deviate significantly from the majority of other observations in a dataset. They lie an abnormal distance from other values, appearing to fall outside the overall pattern. The impact of outliers can be substantial. They can heavily skew statistical analyses, such as means and standard deviations, leading to inaccurate representations of the data. Outliers can also negatively affect the performance of machine learning models, causing them to generalize poorly. Detecting outliers is the first step in addressing them. Several methods are available for identification. Visualizations are often very effective, with box plots clearly showing points outside the whiskers and scatter plots revealing isolated data points. Statistical tests also provide quantitative methods for outlier detection. The z-score measures how many standard deviations an observation is from the mean, with values beyond a certain threshold often considered outliers. The interquartile range, or IQR, method identifies outliers as points falling below Q1 minus 1.5 times the IQR, or above Q3 plus 1.5 times the IQR. Once detected, outliers can be treated in several ways. One option is removal, where the outlier data points are simply deleted from the dataset. This can be appropriate when outliers are clearly due to data entry errors or measurement mistakes. However, a significant limitation of removal is the potential for information loss. If an outlier represents a genuine, albeit rare, observation, deleting it might remove valuable insights. It is crucial to understand the context of the outlier before deciding to remove it. Another treatment method is transformation. This involves applying mathematical transformations to the data, such as a log transformation or square root transformation. These transformations can reduce the impact of outliers by compressing the range of values, making the distribution more symmetrical. Capping or Windsorizing is a technique where outliers are replaced with a predefined maximum or minimum value. For example, all values above the 99th percentile might be replaced with the value at the 99th percentile. This method limits the extreme influence of outliers without completely removing them. Inconsistent data is another pervasive problem that can undermine data quality. Sources of inconsistency include simple typos, different formatting conventions for the same type of data, and conflicting entries across various records. For example, dates might be entered as mm/dd/yyyy in one place and ddmmyy in another. Resolving inconsistencies requires careful attention to detail and systematic application of rules. Standardization is a key technique, ensuring consistent formats across the dataset. This might involve converting all dates to a single format, standardizing address abbreviations, or ensuring units of measurement are uniform. Data type conversion is also crucial. Often, numerical data might be incorrectly stored as strings, or dates as general text. Converting data to its correct type, such as strings to numbers or text to date-time objects, ensures that it can be processed and analyzed appropriately. Duplicate removal is essential for maintaining data integrity. Identifying and eliminating redundant records ensures that each unique entity is represented only once. Duplicates can inflate counts, skew averages, and lead to biased analyses. This often involves defining a set of key identifiers to determine if two records are indeed duplicates. Finally, validation plays a vital role in dealing with inconsistent data. This involves using rules and constraints to ensure data accuracy and adherence to predefined standards. For instance, a validation rule might ensure that age values are always positive, or that email addresses follow a specific format. Beyond these core techniques, two other important data cleaning and preparation steps are often necessary. Data transformation involves scaling and normalizing data. This process adjusts the range of values for numerical features, which can significantly improve the performance of many machine learning models. For example, min-max scaling or z-score standardization are common transformation methods. Encoding categorical variables is another critical technique. Many machine learning algorithms require numerical input. Therefore, non-numerical or categorical data must be converted into numerical representations. One-hot encoding and label encoding are popular methods for achieving this, allowing models to process qualitative information. In conclusion, the selection of appropriate data cleaning techniques depends heavily on several factors. These include the specific characteristics of your dataset, the nature of the errors present, and the ultimate goals of your analysis. There is no one-size-fits-all solution. A tailored approach is almost always required. The data cleaning process is inherently iterative. It often requires multiple rounds of cleaning, validation, and reevaluation as you uncover new issues or refine your understanding of the data. It is a continuous cycle of inspection, transformation, and verification. Overall, data cleaning is not merely a preliminary step but an absolutely essential component of any data-driven project. It is fundamental for building robust and reliable data-driven solutions, ensuring that your insights are accurate, your models perform optimally, and your decisions are well-founded. Mastering these techniques is a cornerstone of effective data science.